Over the next several hours, you are going to travel through more than 160 million years of history. The story begins on a planet still recovering from the worst catastrophe life had ever faced. This was long before dinosaurs existed at all. From there, the story moves through their strange, uncertain beginnings. It moves into an age of true giants. It passes through forests, floodplains, and continents that slowly drifted apart. Eventually, it reaches a single, sudden morning that changed the world forever. One branch of that story never actually ended. By the close of this documentary, you will understand why. There is no need to follow every detail as it passes. You can rest, drift, and return whenever you like. The story will carry on regardless. We begin not with a dinosaur at all, but with the world that made room for them. 252 million years ago, the Earth was recovering from a disaster. Scientists call it the Permian extinction. It remains the most severe loss of life the planet has ever. Hoarded, massive volcanic eruptions in what is now Siberia poured out lava and gas for an extended stretch of time, disrupting the climate, altering the chemistry of the oceans, and driving a widespread loss of atmospheric oxygen. Roughly 9 in every 10 species alive at the time did not survive it. The land that remained was joined into a single supercontinent. Scientists call it Pangaea. One uninterrupted ocean surrounded it, called Panthalassa. The interior of Pangaea lay far from any coastline. Seas normally carry moisture inland, softening a climate. Without that moisture, much of this interior baked under long, dry stretches. These dry periods were broken by short, heavy bursts of rain. Life did not stay diminished for long. Into the empty space left behind, 2 major lineages began to spread. One would eventually lead to mammals. The other was a group of reptiles called archosaurs. Archosaurs would eventually lead to both crocodilians and dinosaurs. For a long stretch of the Triassic period, though, the crocodile-line archosaurs held the advantage. Some of these early crocodile relatives walked upright on 2 legs. Others carried bony armor across their backs. A number of them grew to considerable size. They hunted as the dominant predators of their world. For millions of years, the ancestors of modern alligators simply outcompeted the ancestors of dinosaurs. Alongside them lived early relatives of mammals called synapsids. This lineage had also been reduced nearly to nothing by the Permian extinction, but it had begun, slowly, to recover. One of its more successful early survivors was a stocky, tusked animal called Lystrosaurus. In the millions of years after the catastrophe, it spread across almost the entire supercontinent. New competition eventually pushed it into decline. Other synapsids diversified alongside it. Cynodonts were one such group. They were smaller, more active animals with jaws and teeth that hint at the beginnings of the mammalian body plan, still millions of years away. Some cynodonts grew fur-like coverings. Some may have regulated their own body temperature to a degree long before true mammals appeared. These animals shared the Triassic landscape with the earliest dinosaurs. For a long stretch of time, it was not at all obvious which of these 2 lineages, synapsid or archosaur, would eventually come to dominate the land. It was a strange, unfinished sort of world. No grass grew anywhere on land, since grasses had not yet evolved and would not appear in any meaningful way until deep into the age of dinosaurs. Ferns, mosses, and low conifers covered what ground vegetation there was. Where the climate allowed taller forests, they consisted of conifers, ginkgos, and cycads. Cycads were an ancient group of plants resembling the cross between a palm and a pine cone. Oxygen levels sat lower than they do today. Some researchers connect this detail to a breathing system that would later distinguish dinosaurs from most other animals. It involved a network of internal air sacs branching from the lungs into the skeleton itself. The exact origin of this system remains a subject of ongoing study. Among the crocodile-line archosaurs of this period were some strange animals. To modern eyes, they would look almost nothing like a crocodile. Some, called Rauisuchians, stood tall on upright legs. They hunted much as a large theropod dinosaur would later hunt. They had deep skulls and serrated teeth, suited to bringing down sizable prey. Others, the etosaurs, were armored, low-slung herbivores. Their backs were covered in interlocking plates. They occupied an ecological role that dinosaurs themselves would not fill for millions of years. For a visitor able to walk across this Triassic world, these animals would have looked dominant. They patrolled the floodplains and drier uplands. Their diversity of forms was something dinosaurs had not yet come close to matching. The climate itself shaped daily life in difficult ways. Pangaea's vast interior was cut off from the moderating influence of any nearby coastline. It likely experienced extreme swings between wet and dry seasons. Monsoon-like rains would sweep across certain regions for part of the year. Then they would retreat into long stretches of drought. Riverbeds that ran full during the rains would shrink to scattered pools during the dry months. This concentrated both plant-eating animals and the predators that followed them, gathering around whatever water remained. It was into this unstable, seasonally punishing landscape that the first dinosaurs would need to find their footing. Rock layers from this period preserve traces of ancient soils that formed under these harsh, seasonal conditions, reddish and cracked in a way that still shows, in cross-section, the deep fissures left behind by repeated cycles of wetting and drying. Fossilized burrows also turn up in some of these layers, dug by smaller animals seeking shelter from the heat or from predators, or simply from the difficulty of finding water on the surface during the driest stretches of the year. Even before dinosaurs existed at all, life on this supercontinent had already learned to survive through patience, adaptation, and a willingness to wait out conditions that would not improve for months at a time. Into this recovering, competitive world, the first true dinosaurs would soon appear. Almost nothing about their arrival suggested what they would eventually become. The earliest dinosaurs known from the fossil record appeared around 230 million years ago. They lived in a region that is now northwestern Argentina. The land sat near the equator at the time. Its climate was marked by long dry seasons, broken by short periods of rain. In the layered rock of this period, paleontologists have found the remains of small, two-legged animals. They had lightweight skulls and grasping hands. These animals stand among the earliest confirmed members of the dinosaur lineage. One of the clearest examples is Eoraptor. Its name means dawn thief. It was barely a meter long, likely no heavier than a large house cat. It had small, varied teeth, suited to both plant and animal matter. This suggests that this very early dinosaur had not yet settled into a strict predator's way of life, or a strict herbivore's. Alongside it lived Herrerasaurus. It was larger and more clearly built for hunting, with curved claws and a jaw suited to gripping struggling prey. For years, researchers debated whether Herrerasaurus belonged with the dinosaurs at all, since certain unusual features in its hip bones made the case uncertain, a sign that the boundary separating true dinosaurs from their closest relatives is not always sharply drawn this early in the family tree. What actually defines a dinosaur is a specific set of features in the hip and hind limb. Most reptiles have legs that splay outward to the side. Dinosaurs instead stood with their legs tucked directly beneath the body. This upright posture allowed for longer strides. Eventually, it allowed for far greater body weight than a sprawling stance could ever support. This single structural shift underlies much of what dinosaurs would go on to achieve. A perforated hip socket, open rather than closed at its center, played a role in this shift. So did an inward-turned femur that fits snugly into that socket. Together, these features let dinosaurs walk and run with a fully upright gait. Most other reptiles, both then and now, simply do not share this efficient way of moving. The rock formation preserving these earliest dinosaurs is known today as the Ishigualasto Formation. It records an environment of seasonal rivers, cutting through a landscape of ferns and early conifers. Ash falls from nearby volcanic eruptions occasionally settled across this landscape as well. Alongside Eoraptor and Herrerasaurus lived a wider community of Triassic animals. Early relatives of crocodiles moved through this world. Various synapsids did too. So did a group of smaller, superficially similar reptiles called silsaurs. Silsaurs were close cousins to dinosaurs. They shared many features with them, but fell just outside the group as strictly defined. Some silsaurs walked on all four legs. They had already begun to develop simple plant processing teeth. This hints that even before true dinosaurs diversified, the broader family was already testing different ways of life. For millions of years after they first appeared, dinosaurs remained a minor presence. They lived at the margins of an ecosystem still dominated by crocodile-line archosaurs and various synapsid lineages. Standing on that arid Triassic landscape, one would have seen little to suggest what was coming. Nothing hinted that this small, quick-footed group would someday dominate the planet. They were simply one more experiment among many. They were testing their place in a world still finding its balance after catastrophe. Elsewhere on Pangaea, similar small dinosaurs were beginning to appear as well. They spread gradually along the connected landmass. Nowhere in these early millions of years did they outnumber the older, more established reptile groups sharing their world. Fossils of these early dinosaurs, or of animals very close to them, have since turned up on several other continents, evidence of just how freely animals could move across the connected surface of Pangaea. Similar small, two-legged forms appear in rocks from what is now southern Africa and from what is now India, both regions that sat, at the time, within easy reach of the same unbroken landmass that included modern South America. This wide early distribution stands in real contrast to the more separated, more regionally distinct dinosaur faunas that would develop much later, once the continents had drifted apart. A striking gap in time separates these earliest dinosaurs. from the more familiar species that came later. Eoraptor and Herrerasaurus lived around 35 million years before Tyrannosaurus rex. This is a longer stretch of time than separates Tyrannosaurus from the present day, more than twice as long. In fact, the dinosaur family had an immense amount of history still ahead of it when these first small two-legged animals were testing their footing on the dry floodplains of ancient Argentina. Far more history than had passed by the time the group finally reached its most famous and most recognizable forms. That balance was about to break again. Around 201 million years ago, Pangaea began the long process of splitting apart. A new wave of massive volcanic eruptions came with it. These eruptions released enormous quantities of gas into the atmosphere over a fairly short span of geological time. This event is now known as the end, Triassic extinction. It struck the crocodile-line archosaurs with particular severity. It struck a number of other dominant Triassic groups too. Dinosaurs, for reasons still debated among researchers, came through it in a stronger position. The eruptions responsible for this extinction are linked to a vast volcanic region called the Central Atlantic Magmatic Province. It formed as Pangaea began to tear apart along the line that would eventually become the Atlantic Ocean. The gases released included large volumes of carbon dioxide and sulfur compounds. These gases appear to have driven rapid shifts in global temperature. They shifted ocean chemistry too. This placed severe strain on animals already adapted to the specific conditions of the late Triassic world. Many of the large Rauisuchians and Etosaurs that had dominated their landscape for tens of millions of years do not appear in the fossil record after this point. No animal living through this transition could have understood what was happening. Nothing told them that the disappearance of so many established competitors was clearing the way for something new. Dinosaurs had, until then, been a minor part of the landscape. But with their rivals diminished, they began to spread further, grow larger, and diversify into a widening range of forms. Early sauropod ancestors, small theropods, and the first plant-eating ornithischian dinosaurs all expanded their range during the millions of years after this extinction, moving into ecological roles that had, until recently, belonged to other animals entirely. The pterosaurs benefited from this same clearing of the field as well, growing more diverse through the earliest part of the Jurassic period. During the Triassic, they had shared the skies with several other, less successful lineages of gliding reptile, and those lineages did not survive the transition. The pattern seen at the end of the Triassic would, in a sense, repeat itself again and again across the history of life on this planet. A dominant, established group holds its ground for millions of years, seemingly secure, until a sudden environmental shock removes it from the picture almost entirely, clearing space for whichever group happens to be positioned to take advantage of the opening. Dinosaurs benefited from exactly this kind of opening at the close of the Triassic. Much later in this same documentary, dinosaurs themselves would find their own dominance ended by an almost identical process, though driven by a very different kind of catastrophe entirely. This extinction also reshaped the plant life covering Pangaea in ways that would matter a great deal for the herbivores soon to follow. Certain conifer families that had dominated the Triassic landscape declined sharply, replaced gradually by other conifer groups better suited to the wetter, more humid conditions that followed. Ginkgos, a plant family still represented today by a single surviving species, spread widely during this period as well. Their broad, fan-shaped leaves becoming a common sight across the early Jurassic landscape. This shifting plant life would, in the following chapter, help set the stage for the rise of the very first giant sauropods, animals whose enormous size depended directly on having enough of the right kind of vegetation available to sustain them. By the opening of the Jurassic period, roughly 201 million years ago, the world lay open to dinosaurs in a way it never had before. The early Jurassic world differed from the one before it. Pangaea continued to pull apart, and shallow seas crept into the widening gaps between its fragments. The increased coastline brought more rainfall further inland than the dry Triassic interior had ever received, and forests thickened in response. Ferns spread across lowland floodplains, while conifers grew tall along the higher ground. For plant-eating animals, opportunity had arrived. It was during this period that one of the most recognizable dinosaur body plans began to take shape. These were the long-necked, long-tailed sauropods. Their ancestors had already appeared in smaller form during the late Triassic. Some of them could still rear onto their hind legs to browse. Across the following millions of years, these animals shifted permanently onto four legs. They grew heavier. They stretched their necks further from their bodies than almost any land animal before or since. A long neck solved a particular problem efficiently. An animal that could sweep its head through a wide arc did not need to move its enormous body to reach new food. It could browse many trees or many heights on a single tree from one fixed spot. This spent far less energy than walking to each new feeding spot. For an animal that needed enormous quantities of plant material every day, this mattered enormously. It set the stage for a body plan that would soon reach sizes unlike anything the world had produced before. Before true sauropods reached their full size, a related group called the sauropodomorphs, sometimes informally called prosauropods, filled a transitional role during the very late Triassic and earliest Jurassic. Plateosaurus, one of the better-known examples, could reach lengths of around 8 meters, significantly larger than most other animals of its time, and likely alternated between walking on 2 legs and 4 depending on its speed and the terrain. Its hands, though adapted for a largely plant-based diet, retained a sharp thumb claw, possibly useful for defense or for pulling down branches, a feature that hints at how gradually the specialized, fully quadrupedal sauropod body plan actually came together rather than appearing in a single evolutionary step. The forests these early sauropods moved through would have smelled unfamiliar to modern noses. Cycads grew in dense stands close to the ground. Their stiff, palm-like fronds formed a coarse understory beneath towering conifers. Some of these conifers were related to species such as monkey puzzle trees, still alive today. Horsetails and ferns filled the damp margins along rivers and lakes. They offered a softer, more easily cropped source of food than the tougher conifer needles above. Early in the Jurassic, this vegetation had not yet been shaped by the grazing pressure of enormous herbivores. As sauropods began moving through these landscapes in greater numbers, the plant life itself would gradually have begun to change. Not every herbivore of this period grew large. Small, lightly built plant eaters moved through the same undergrowth as the emerging sauropod lineages. Scutellosaurus and Lesothosaurus were 2 such animals. They were covered in rows of small bony studs along the back. This was an early, modest version of the armor that later ankylosaurs and stegosaurs would carry to far greater extremes. These small herbivores likely relied on speed to avoid predators. They also relied on staying low and hidden among the ferns. This was quite different from the sheer bulk their larger sauropod relatives were beginning to rely on instead. Even at this early stage, dinosaurs were already testing more than one solution to the same basic problem. That problem was simply staying alive long enough to reproduce. The early Jurassic was not without its own disruptions. Around 183 million years ago, a period of widespread ocean deoxygenation struck the seas, an event researchers now call the Toarcian anoxic event. It appears to have been driven by a separate pulse of volcanic activity, this time centered in what is now southern Africa. Marine life suffered significantly during this period, and global temperatures rose sharply for a time. Its effects on dinosaurs themselves remain harder to trace directly, since the fossil record from this exact window is comparatively thin, though it shows that the early Jurassic, for all its opportunity, was not a perfectly stable world either. Change, in one form or another, was a constant companion to every stretch of this long history. By the middle and later parts of the Jurassic period, sauropods had spread across most continents. They diversified into many distinct forms. The Morrison Formation is a rock unit spanning much of the western United States. It preserves an unusually rich record of this world. Diplodocus lived here with its extremely long whip-like tail. So did Brachiosaurus, whose front legs were longer than its hind legs. This tilted its body upward. It let the animal browse from heights approaching 12 meters, well above the reach of almost anything else alive at the time. The largest sauropods weighed somewhere between 10 and perhaps 20 or more tons, depending on the species. An enormous mass to sustain, given how small their heads were and how simple and peg-shaped their teeth remained, poorly built for grinding. The likely answer is that most sauropods barely chewed at all, stripping leaves from branches and swallowing them close to whole, relying on an extended digestive process to break the material down slowly over time. Smooth, rounded stones, called gastroliths, are sometimes found alongside sauropod skeletons, and for a long time, researchers assumed these functioned much like the grinding stones found in the gizzards of modern birds, helping to break down tough plant fibers inside the gut. More recent studies have called this comparison into question, since the number and wear pattern of stones found with sauropod skeletons often does not match what a dedicated grinding gizzard would produce, and their true function, digestive aid, incidental swallowing, or something else entirely, remains an open question. Much of what made this scale possible lay hidden within the skeleton itself. Many sauropod bones, especially through the neck and spine, were not solid. They were honeycombed with air-filled pockets. These pockets connected to a network of air sacs branching from the lungs. This kept the skeleton much lighter than a solid structure of equal size would have been. It still remained strong enough to bear the animal's weight. This was one of several quiet advantages behind the sheer size these animals reached. Bone histology is the microscopic study of bone tissue. It has added further detail to this picture. Growth rings preserved within sauropod bones work much like the rings found in a tree trunk. They suggest that many of these animals grew at an unusually fast pace during their early years. Many reached a large share of their adult size within a fairly short number of years. This differs from most living reptiles, which grow gradually across an entire lifetime. Not every sauropod followed the same design. Diplodocus carried an unusually long, whip-thin tail. Some researchers have proposed it could have been snapped or cracked as a defensive or communicative gesture. This idea remains difficult to confirm from fossil evidence alone. Others developed more compact proportions. Camarasaurus, another Morrison Formation resident, had a shorter neck than its relatives. It had a deeper, more heavily built skull. Its teeth were stronger and spoon-shaped. This suggests it fed on tougher vegetation, closer to the ground than the towering canopy favored by Brachiosaurus. Different species feeding at different heights or on different plants likely let several enormous herbivores share a single landscape. They did not need to compete directly for the same limited resources. Growth ring evidence also lets researchers estimate roughly how long individual sauropods lived. Some studies suggest lifespans reaching several decades, shorter than the centuries sometimes assumed in older, more speculative accounts. Even so, it was long enough for a single animal to witness real change across its own lifetime, as forests shifted and rivers changed course, while the slow Jurassic landscape kept transforming around it. Not every sauropod grew to the sizes described so far. Europasaurus, discovered in what is now Germany, offers a striking exception. It lived on a small island within a late Jurassic archipelago, isolated from the mainland by shallow seas. Adults reached only around 6 meters in length, a fraction of the size typical for its close relatives. This appears to be an early example of island dwarfism among sauropods, a pattern that would repeat itself among other isolated dinosaur populations much later in the Cretaceous. Limited food on a small island evidently placed real limits on how large even a sauropod could safely grow. Picture the edge of a Jurassic floodplain late in the afternoon. A scattered group of sauropods moves along a riverbank. Their necks sway above the tree line as they feed. The ground trembles faintly beneath the largest animals with each step. Dust hangs briefly in the air behind a passing herd. Then it settles back over cycad fronds and fallen conifer needles. It was a world built on a different scale entirely. That scale had been building for tens of millions of years. As prey animals grew larger through the Jurassic, the predators hunting alongside them faced pressure of their own. They needed to keep pace. Early theropods appeared alongside the first dinosaurs in the Triassic. They had generally been small and lightly built. As the Jurassic progressed, certain theropod lineages grew much larger in response to their growing prey. Allosaurus was one of the best-known Jurassic predators. It reached lengths of around 9 meters. Its skull was built for fast, slashing bites rather than a single crushing hold. It struck and pulled back to open a wound rather than clamping down and refusing to let go. It was far from the only predator of its world. Still, it stands as one of the clearest examples of how theropods adapted to the growing scale of Jurassic herbivores. Those herbivores, for their part, did not rely on size alone. Among the most distinctive Jurassic plant eaters were the stegosaurs. Stegosaurus itself is the best example. A row of large flat plates ran along its spine, sharp spikes extended from the end of its tail. The function of the back plates remains debated. They may have assisted with temperature regulation, since they were filled with blood vessels. These vessels could absorb or release heat. The plates may also have served a visual role. They could have signaled maturity or fitness to potential mates or rivals. They may have made the animal look larger to an approaching predator too. These explanations are not mutually exclusive. The true answer may involve more than one function at once. The tail spikes present a more straightforward case. Fossil evidence supports this. Some predator bones bear puncture wounds that match the spacing of these spikes. This suggests Stegosaurus used its tail as an active weapon. It swung the tail with enough force to injure an attacking theropod. It was one of the more direct forms of defense to appear during this period. It would not be the last. The earliest members of another armored lineage also appeared during the later Jurassic. These were the Ankylosaurs. This group would not reach its full diversity until well into the following period. Early Ankylosaurs were low and wide-bodied. Bony plates covered their backs and sides, embedded directly in the skin. These early forms represented the beginning of a defensive strategy. Later relatives would carry it significantly further. Allosaurus was not the only theropod hunting across the late Jurassic landscape. Smaller, swifter predators moved through the same forests and floodplains. Ornitholestes and Coelurus were two such animals. They likely targeted small animals, early mammals, and juvenile dinosaurs, prey that larger predators would have overlooked. A somewhat larger contemporary, Ceratosaurus, carried a distinctive blade-like horn on its snout. A row of small bony plates ran down its back. It may have specialized in hunting near rivers and lake margins. Aquatic prey has occasionally been found associated with its remains. This layering of predator sizes meant that almost no size class of animal in this ecosystem was entirely free from predation. Over the following tens of millions of years, this pressure would continue to shape both hunter and hunted in an unbroken evolutionary exchange. The plants of this same landscape carried their own defenses against the growing pressure of large-bodied herbivores. Many conifers of the Jurassic period produced tough, resinous needles, difficult to digest and low in nutritional reward compared to the softer growth found on ferns and horsetails. Some researchers suggest that this relatively poor nutritional quality may help explain something. Sauropods needed to consume such an enormous daily volume of plant matter in the first place because of it. A diet built largely around low-quality conifer browse would require far greater bulk intake than a diet built around richer, more digestible vegetation. In this sense, the plants and the animals that fed on them were locked in their own slower, quieter version of the same evolutionary exchange playing out between predator and prey. Stegosaurs were not confined to North America. Kentrosaurus was a smaller relative of Stegosaurus, discovered in what is now Tanzania. It carried a similar row of plates along its shoulders. Further down its back and tail, these gave way to long, sharp spikes rather than flat plates. This suggests that different stegosaur lineages balanced the display and defensive roles of their armor somewhat differently. Their choices likely depended on their particular predators and environment. Miragaia, discovered in Portugal, offers a further surprise within this same family. Unlike most stegosaurs, it carried an unusually long neck made up of at least 17 vertebrae, roughly twice the number found in its closer relatives. Researchers are not entirely certain why this lineage stretched its neck in this particular direction, since stegosaurs generally fed on low vegetation rather than the towering canopy favored by sauropods. One possibility is that a longer neck simply let Miragaia reach a wider spread of ground-level plants without needing to move its body as often. A smaller echo of the same basic advantage that shaped the necks of its much larger sauropod neighbors. Dinosaurs, by strict definition, were land animals. Aside from birds, the group never produced a lineage capable of true powered flight. Even so, the world of the dinosaurs was never confined to land alone. Overhead and offshore, an entirely separate branch of reptiles had been adapting to life in the air and in the water. This began well before the Jurassic. These animals are worth understanding clearly. They are often mistaken for dinosaurs in popular imagination, despite belonging to a distinct part of the reptile family tree. Pterosaurs were the flying reptiles. They first appeared during the late Triassic period, around the same general time as the earliest true dinosaurs. They would persist for the entire remaining span of the Mesozoic era. Early pterosaurs were generally small. An elongated fourth finger on each hand supported them. It anchored a thin skin membrane, stretching back to the body and legs. By the Jurassic, pterosaurs such as Rhamphorhynchus and Pterodactylus patrolled the shallow seas and lagoons of what is now Europe. Rhamphorhynchus had a long, narrow tail, ending in a diamond-shaped vein. Pterodactylus was nearly tailless, with a shorter, more compact skull. Together they show two rather different solutions to controlled flight within the same broad family. Later in their history, some pterosaur lineages would grow to sizes far beyond anything seen in the Jurassic. These Jurassic pterosaurs likely fed largely on fish, snatched from the surface of the water during low, gliding passes. Their long jaws lined with narrow, needle-like teeth, well suited to gripping a slippery catch. Fossilized stomach contents recovered from a small number of exceptionally well-preserved specimens have confirmed fish scales and small bone fragments in at least a few individuals, offering direct evidence to support what their jaw structure alone had already suggested. Some smaller pterosaurs may instead have specialized in catching insects on the wing. Their proportionally shorter, more delicate jaws better suited to this smaller, more agile prey than to wrestling a struggling fish from open water. Beneath the ocean's surface, the ichthyosaurs had taken a strikingly different path. They adapted so thoroughly to aquatic life that they could no longer return to land at all. Their streamlined bodies, flippers, and tail fins closely resembled those of modern dolphins. The two groups were entirely unrelated, separated by hundreds of millions of years. They belonged to different classes of animal altogether, one reptile, one mammal. This kind of independent evolution toward a similar body shape is called convergent evolution. It happens when shared environmental pressure, rather than shared ancestry, produces a similar result. The resemblance between ichthyosaurs and dolphins remains one of its clearest examples in the fossil record. Ichthyosaurs reached their greatest diversity during the Triassic and Jurassic periods. They declined sharply by the middle of the Cretaceous. They disappeared well before the extinction that eventually closed the age of dinosaurs. Jurassic seas also supported other marine reptiles, less familiar to popular imagination. Metriorhynchids were a group of crocodile relatives. They had adapted so fully to ocean life that their limbs became paddle-like flippers. Their tails developed a sharp-like fin. This was an entirely separate example of the same convergent process that shaped the ichthyosaurs. These marine crocodile relatives hunted alongside ichthyosaurs. They shared the water with the earliest plesiosaurs too, in the shallow seas that now cover parts of Europe. This period has left behind some of the most complete marine reptile fossils known anywhere. Alongside them swam the plesiosaurs. They were generally broader-bodied with 4 flippers. Many species had an unusually long neck, extending from a small head. Some plesiosaur necks contained well over 70 individual vertebrae. Their close relatives, the pliosaurs, took the opposite approach. They had shorter, more powerful necks and enormous jaws. These jaws suited them to hunting larger prey. This sometimes included other marine reptiles. None of these animals were dinosaurs. Not the pterosaurs above, nor the ichthyosaurs, plesiosaurs, and marine crocodile relatives below. They were distant reptile cousins. They followed their own evolutionary paths through the same span of time. Together with the dinosaurs themselves, they formed a broader Mesozoic world. It extended from the driest interior deserts to the deepest reaches of the open ocean. The seas of this period supported more than just reptiles. Ammonites, distant relatives of modern squid and octopus, drifted through Jurassic waters in coiled, chambered shells that ranged from the size of a coin to well over a meter across in some later species. Belemnites, another related group, resembled a squid with an internal, bullet-shaped shell, and their remains are so common in certain rock layers that entire beaches in parts of England are still scattered with their fossilized remnants today. These smaller, less dramatic animals formed much of the base of the marine food web that ichthyosaurs, plesiosaurs, and marine crocodile relatives ultimately depended on, since the largest and most striking animals of any ecosystem rarely tell the whole story on their own. For much of the history of paleontology, dinosaurs were pictured as entirely scaled animals. This picture has changed a great deal over the past few decades. Fossil discoveries from several regions have shown otherwise. Certain rock formations in northeastern China have been especially important. They have revealed dinosaurs preserved with clear impressions of feathers and feather-like filaments across their bodies. Feathers appear to have been widespread specifically among theropods, the meat-eating branch of the dinosaur family that includes the ancestors of birds, and there is little evidence that large plant-eating groups such as sauropods or ceratopsians carried feathers at all. Among feathered theropods, Angionis stands out, a small animal from the late Jurassic of China weighing under half a kilogram. It is known from an unusually large number of well-preserved specimens, which has let researchers reconstruct its plumage with real confidence. Grey and black feathers covered its body. A reddish crest sat atop its head, and white wing feathers were marked with dark spots. A close relative, Epidexipteryx, carried 4 long ribbon-like tail feathers. These were distinct in shape from typical flight feathers. They were poorly suited to any aerodynamic purpose. Researchers generally interpret them as a display structure. They may have been used to attract mates or to signal to other members of the same species. This falls in the same broad category as the elaborate, non-functional tail feathers of certain modern birds. The presence of feathers well before flight existed points toward an original purpose, unrelated to flying at all. Several explanations have gained support, and they are not mutually exclusive. Feathers may have first evolved for insulation, helping smaller, more active theropods regulate their body temperature. They likely also served a role in display, since fossil feathers sometimes preserve traces of color-bearing structures called melanosomes, which let scientists reconstruct probable coloring in certain species with reasonable confidence. The structure of feathers themselves appears to have developed in stages. This happened across many millions of years, rather than appearing all at once in a finished form. The simplest feathered dinosaurs known from the fossil record carried little more than hollow hair-like filaments. These were closer to bristles than to a true feather. Later forms developed a central shaft with branching barbs. Later still came the interlocking, zippered structure seen in modern flight feathers. This structure can form a smooth, air-resistant surface. Each of these intermediate stages appears in different dinosaur lineages, at different points. Some of these lineages were large-bodied and entirely flightless. This suggests the structure evolved gradually, for reasons unrelated to flight, long before any lineage put it to that particular use. Archaeopteryx was discovered in Germany in the 19th. Curie. It remains one of the most significant transitional fossils ever found. It dates to the very end of the Jurassic period. It combined feathered wings, similar to those of a bird, with features otherwise associated with non-avian dinosaurs. These included teeth, a long, bony tail, and clawed fingers. Rather than a single dramatic transformation, the fossil record suggests a gradual drift. This drift took place across many millions of years. Feathers were useful in one form or another long before flight itself became possible. Whether Archaeopteryx itself could manage true, sustained flapping flight remains debated. Researchers who study its wing and shoulder structure closely are divided. It may instead have been capable of something closer to an extended glide, punctuated by weak wing beats. What is clearer is that it lived alongside several other small feathered theropods. These animals shared similar habitats along the shallow lagoons of what is now southern Germany. By the very end of the Jurassic, a whole community of small, bird-like dinosaurs had already begun exploring the space between running, gliding, and true flight. No single lineage made this transition alone. The limestone deposits that preserved Archaeopteryx formed under unusually calm, still conditions, in a lagoon cut off from the open sea by a barrier of coral and sponge reefs. Very little oxygen reached the lagoon floor, which meant scavengers rarely disturbed a carcass before fine sediment could settle over it, preserving delicate structures such as feathers that would ordinarily decay or scatter long before fossilization had any chance to begin. This same unusual combination of conditions has preserved a wide range of other Jurassic life from this region in exceptional detail, including fish, insects, and even the occasional jellyfish, offering a level of completeness rarely matched anywhere else in the entire Mesozoic fossil record. By the close of the Jurassic period, one small feathered corner of the theropod family had begun a path. Tens of millions of years later, it would lead to modern birds. This is a thread that runs continuously through the remainder of this documentary. The color patterns reconstructed from these early feathered dinosaurs deserve a moment of their own attention. Beyond the banded tail of Sinosauropteryx and the crested plumage of Anchiornis, researchers examining Microraptor's feathers found evidence pointing toward an iridescent, glossy black sheen, not unlike the sheen seen on modern crows or grackles when light catches their feathers at the right angle. This kind of coloring depends on the precise physical structure of the feather itself, rather than on pigment alone. Its presence in a dinosaur this early suggests that the biological machinery for producing structural color, not just simple pigment-based color, had already developed well before birds themselves existed in their modern form. The Jurassic period gave way to the Cretaceous around 145 million years ago. There was no single dramatic marker for this shift. It was simply a continuation of the same slow drift of continents and climate, already underway, in what is now northeastern China. An unusual set of conditions produced one of the richest fossil records anywhere in the world for this period. Periodic volcanic ash falls buried entire ecosystems quickly in fine detail. Researchers generally call this record the J-hole biota. Among its most striking discoveries is Microraptor. It was a crow-sized dinosaur with long flight feathers, not only on its arms, but on its legs as well. This gave it what researchers describe as a four-winged body plan. Current evidence suggests Microraptor could glide between trees. It likely used all four limbs to help control its movement through the air. This represents an intermediate stage, somewhere between flightless theropods and animals capable of sustained, powered flight. Even stranger is Yichi, a pigeon-sized dinosaur. Its name means strange wing, rather than a wing built from feathers. Yichi appears to have had a membrane of skin. This membrane stretched between an unusually long, rod-like bone, extending from its wrist and its finger bones. The structure is closer in basic design to the wing of a bat than to the wing of a bird. Whether it allowed any meaningful gliding remains uncertain. Its existence shows that at least one dinosaur lineage experimented with an entirely different solution for getting off the ground. Sinosauropteryx was another J-hole discovery. It was the first dinosaur for which scientists reconstructed likely color patterning from preserved melanosomes. This revealed a banded, reddish-brown and pale tail. The J-hole ecosystem as a whole preserves an unusually complete snapshot of an early Cretaceous world. Early flowering plants were beginning their spread. Freshwater fish, salamanders, and small mammals lived here too, along with an abundance of insects. All of it was buried together in the same fine volcanic ash that captured its dinosaurs in such detail. Lakes fed by nearby volcanic activity would periodically release pulses of toxic gas. Some of the most completely preserved fossils from this region appear to have died suddenly, still caught in the postures of ordinary daily life. Around the same general period, in what is now the western United States, a mid-sized theropod called Deinonychus was hunting. It was discovered in the 1960s. It carried a large, sickle-shaped claw on the second toe of each hind foot. This claw stayed raised clear of the ground while running. It came down with force during an attack. Detailed study of Deinonychus reshaped scientific understanding of dinosaurs more broadly. It suggested active, agile predators rather than the sluggish animals of earlier popular imagination. This shift in thinking is sometimes called the dinosaur renaissance. Multiple Deinonychus individuals have occasionally been found associated with the remains of a single, much larger herbivore. Some researchers have read this as evidence of coordinated group hunting, though, as with similar cases across the theropod family, this interpretation remains contested rather than settled. Yutyrannus lived during this same period. It was an early relative of Tyrannosaurus, significantly larger than most of its feathered relatives. It was discovered in the same fossil-rich region of China. Long, simple, hair-like feathers covered much of its body. This is despite the animal weighing over a ton and reaching lengths of around 9 meters. It lived in a comparatively cool part of the world. This may help explain why insulation remained useful even at this considerable size. Whether its much later relative, Tyrannosaurus rex, retained any feathers is truly uncertain. Tyrannosaurus lived in a warmer climate. The Jehol biota preserves early birds as well as feathered non-avian dinosaurs. This offers a useful point of comparison between the two. Confuciusornis is among the earliest known birds. It had a toothless, horn-covered beak rather than the tooth-lined jaws of Archaeopteryx. It is known from thousands of individual fossils. Some preserve a pair of unusually long, ribbon-like tail feathers. These appear only in what seem to be male specimens. This is an early hint of the kind of sex-based visual display still common among birds today. Psittacosaurus, an early relative of the horned ceratopsian dinosaurs, adds a further surprise. At least one specimen preserves a row of long, hollow, quill-like bristles projecting from the top of its tail. These are structurally distinct from true feathers. They suggest that filament-like coverings may have been more widespread across the dinosaur family tree than feathers alone. A further Jehol discovery, Jinyuanlong, adds to this picture in a different way. It was a close relative of Velociraptor, but noticeably larger than most of its dromaeosaurid cousins, and preserved with an extensive covering of well-developed wing feathers, despite showing no clear signs of ever having flown. Its wings appear too short and its body too heavy for sustained flight, suggesting the feathers instead served a role in display, or perhaps assisted with balance and maneuvering while running. A separate line of research examined the teeth of a related dromaeosaurid, Sinornithosaurus, and proposed that grooved teeth and a nearby gland might indicate a mild venom delivery system, similar in principle to certain modern lizards. This idea has met with considerable skepticism from other researchers, who argue the same features can be explained without invoking venom at all, and it remains one of the more contested proposals to emerge from this remarkable fossil record. Beyond China, the early Cretaceous world was already beginning to show the kind of regional variation that would deepen further as the period progressed. In what is now Australia, small ornithopod dinosaurs were adapting to a cooler, more seasonal environment than almost anywhere else on the planet at the time, a story explored more fully in a later chapter. In North America, early tyrannosauroids, smaller and less dominant than their famous late Cretaceous descendants, hunted alongside early relatives of the horned and armored dinosaurs that would eventually come to define the region's later fauna. None of these lineages had yet reached the size or diversity they would achieve tens of millions of years later. But the basic outline of the late Cretaceous world, predator families, herbivore families, and the broad ecological roles each would come to occupy, was already visibly taking shape. Throughout the period covered so far, the story of the dinosaurs largely unfolded across a shared landmass. Even so, the slow physical drift of the continents shaped that story more deeply than a simple timeline can easily convey. At the dawn of the dinosaur age, Pangaea let early populations spread across a single unbroken span of land. This land stretched from what is now South America to what is now Asia. That connection did not last, beginning gradually in the late Triassic and accelerating through the Jurassic and Cretaceous. Pangaea split first into two large landmasses. Laurasia sat in the north, Gondwana sat in the south. These fractured further still into an arrangement closer to the modern map. Even so, the continents sat quite differently from where they rest today. As growing stretches of ocean separated populations that had once belonged to a single connected group, those populations began to evolve along increasingly distinct paths. They adapted to their own local climate, geography, and available food. This isolation helps explain why the Cretaceous world shows such a different mix of dinosaur species from one continent to another. The Triassic and early Jurassic, by contrast, show more broadly similar populations across the whole of Pangaea. South America separated relatively early from Africa as Gondwana broke apart. It developed its own titanosaur lineages. Argentinosaurus was among them. Some researchers estimate it exceeded 30 meters in length. These estimates remain provisional, since a complete skeleton has never been recovered. Meanwhile, the continents that would become North America, Europe, and Asia developed their own distinct mix of duck-billed and horned dinosaurs. South America produced far more than just its record-breaking titanosaurs. Giganotosaurus, a large predatory theropod discovered in Argentina, rivaled Tyrannosaurus in length, though the two animals never crossed paths, separated as they were by both distance and tens of millions of years. Unlike Tyrannosaurus, Giganotosaurus belonged to an entirely separate branch of the theropod family, more closely related to Carcharodontosaurus than to any tyrannosaur, since gigantic predatory theropods evolved more than once in different regions and at different points in time, arriving at broadly similar solutions to the same basic problem of hunting very large prey without sharing an especially close common ancestor. India presents a distinctly unusual case. It had broken away from the rest of Gondwana, but had not yet collided with Asia. That collision would not occur until well after the dinosaurs had gone extinct. It would eventually push up the Himalayas. India spent much of the Cretaceous as an isolated island continent, drifting northward on its own. Its dinosaur fauna, including certain titanosaur lineages, shows closer ties to South American and African relatives than to the dinosaurs found in nearby Asia during the same period. This reflects its earlier connection to those southern landmasses before its long isolation began. Africa developed its own distinctive character during this period of separation as well. It supported large-bodied theropods such as Spinosaurus, along with sauropods and early ceratopsian relatives quite different from those found further north. Madagascar split away from both Africa and India during the Cretaceous. It developed its own isolated fauna, including unusual, short-snouted crocodile relatives and theropods found nowhere else. This pattern of island-like isolation, producing unusual, locally distinctive animals, would repeat itself across several separating landmasses throughout the Cretaceous period. Europe offers perhaps the clearest illustration of this pattern, in miniature. For part of the late Cretaceous, much of what is now Romania formed a scattered archipelago of islands within a shallow sea. Researchers now call this environment Hateg Island. Dinosaurs stranded on these islands were cut off from the wider mainland populations they had descended from. Over time, they evolved toward noticeably smaller body sizes. This pattern is called island dwarfism. It is well documented among mammals on modern islands. It was evidently at work among dinosaurs as well. Tyrannosaurus was a hadrosaur relative found here. Magyarosaurus was a titanosaur. Both reached only a fraction of the size typical of their mainland relatives. This adaptation was likely driven by the limited food resources available within such a constrained, isolated environment. Australia and Antarctica present a different kind of isolation story. For much of the Cretaceous, these two land masses remained joined together, sitting far further south than either occupies today. Dinosaurs living here experienced a truly different climate from almost anywhere else on the planet, with a lower sun angle and, for at least part of the year, an extended period of darkness. This southern landmass eventually separated. That process was not fully complete until well after the age of dinosaurs had ended. The animals living on each side found themselves gradually cut off from one another as well. It added yet another chapter to the broader pattern of continental drift, reshaping which populations could reach, which other populations, and when. Not every theropod followed the same evolutionary path. As the Cretaceous progressed, several lineages branched away from the typical model of a fast, purely carnivorous predator. They developed feeding strategies, unlike almost anything else in the dinosaur world. Spinosaurus lived in what is now North Africa roughly 95 million years ago. It carried a tall sail of skin and bone along its back. Its skull was long and narrow, filled with conical teeth. This shape resembles a crocodile's skull more than the skulls of most other theropods. Bone density studies have examined this animal closely, so has the structure of its tail. Some researchers propose that Spinosaurus spent considerable time in or near water, feeding largely on fish. The full extent of this aquatic lifestyle remains debated. Some researchers question whether the animal could sustain real swimming at all. It may instead have waded and foraged along shorelines. What most researchers agree on is simpler. Its diet leaned heavily toward fish and other aquatic prey. This was an unusual specialization for a theropod of its size. A smaller relative, Baryonyx, was discovered in southern England. It offers more direct evidence for this fish-eating lifestyle. Its skull was less specialized than that of Spinosaurus. Even so, it shared the same long, narrow, crocodile-like shape. The original skeleton was recovered with fish scales still preserved in the stomach region. This is among the clearest direct evidence available anywhere in the dinosaur fossil record for what a particular individual had actually eaten shortly before death. Baryonyx also carried an enormous curved claw on each hand. This may have served to hook or spear fish from shallow water. It would otherwise seem an oversized tool for its body. A close cousin of Baryonyx, Sauropods, lived in what is now Niger and shared much of the same basic body plan, including the long, narrow, crocodile-like skull and the large hooked claw on each hand. Its name means crocodile mimic, a fitting description given how closely its head resembled that of a modern crocodilian, despite the two animals being entirely unrelated. Fish fossils from the same region grew unusually large during this period, some reaching lengths comparable to a small car, and it is easy to imagine an animal built like Sauropods finding no shortage of substantial prey along the rivers of this ancient landscape. Tyrannosaurus took an even more distinctive path. Its curved claws exceeded half a meter in length in some cases. This might suggest a formidable predator, yet the available evidence points to a primarily plant-based diet. It had a wide, pot-bellied torso, suited to digesting large volumes of vegetation. This was quite unlike the lean build of most meat-eating relatives in its family. The claws may have served for pulling down branches. They may have served for defense. Perhaps both. The ornithomimosaurs are sometimes called ostrich-mimic dinosaurs. This is for their resemblance to modern flightless birds. They developed long, slender legs suited to speed. Small, toothless beaks completed the picture. Their diets likely combined small animals, insects, seeds, and plant material. For decades, one member of this group remained a genuine mystery. Dinosaurus was known from the 1960s only by a pair of enormous arms exceeding 2 meters in length. It was not fully understood until more complete remains surfaced decades later. These remains revealed an unusually large humpbacked animal. A broad, duck-like snout suited it to feeding on both plants and small aquatic prey. Alongside these unusual specialists, more conventional mid-Cretaceous predators continued to hunt in familiar ways. Triceratops was a large theropod. It lived in North Africa around the same time as Spinosaurus. Its teeth were blade-like and serrated, suited to slicing through flesh. This design is closer to Allosaurus than to the fish-eating adaptations of its sailback neighbor. Its presence alongside Spinosaurus suggests that at least 2 very differently adapted apex predators may have shared parts of the same region, likely dividing the landscape by targeting different prey, one favoring large land animals, the other leaning toward the rivers and coastal waters nearby. These lineages show that the basic theropod body plan, for all its advantages as a predatory design, remained flexible enough to be reshaped repeatedly toward fishing, plant-eating, and omnivory, whenever local conditions favored a different strategy. A further group, the oviraptorosaurs, extended this flexibility even further. Most members of this family had lost their teeth entirely, replacing them with a toothless, parrot-like beak suited to a broad diet of plants, seeds, small animals, and eggs. Tyrannosaurus and its relatives show a wide range of beak shapes across this group. Some suited to crushing tough seeds, others to a more general, opportunistic diet, mirroring the same kind of dietary specialization seen among many modern birds today. Along with Tyrannosaurus and the ornithomimosaurs, the oviraptorosaurs make clear that by the middle of the Cretaceous, a sizable portion of the theropod family had moved well away from the pure predatory lifestyle usually associated with this branch of the dinosaur tree. Roughly 130 million years ago, partway through the Cretaceous period, a new kind of plant began to spread across the landscape. These were flowering plants, known scientifically as angiosperms. For the entire span of the Triassic and Jurassic before this point, land plants had consisted of ferns, conifers, cycads, and similar groups. None of these produce flowers at all. The rise of flowering plants sent effects rippling outward through the wider ecosystem. These plants generally grow and reproduce faster than older plant groups. Many rely on insects for pollination, offering nectar and pollen as reward. Their spread likely supported an increase in insect diversity across the Cretaceous world. This, in turn, likely supported a broader range of small animals feeding on those insects. it layered the food web in ways the earlier, fern and conifer-dominated landscape had not supported. Some researchers connect this shift to changes seen among plant-eating dinosaurs later in the Cretaceous. This is especially true for the emergence of duck-billed dinosaurs with increasingly sophisticated dental batteries. These consisted of hundreds of interlocking teeth, capable of grinding tough plant material with real efficiency. New teeth continuously replaced worn ones throughout the animal's life. Ceratopsians, the horned dinosaurs, developed a different solution. Their teeth were tall and blade-like, arranged for shearing through especially tough fibrous vegetation such as cycads. This let them specialize in plants that other herbivores found harder to process. It reduced direct competition between the two groups. Bees appear to have emerged during this same general window, alongside a growing variety of flowering plant families. Fossilized amber from the Cretaceous period has preserved an unusually detailed record of the insects sharing this changing world. Early ants and wasps show up in this record. So do a range of pollinating beetles, caught mid-visit at a flower, their bodies dusted with grains of ancient pollen still identifiable today. This relationship between flowering plants and their insect pollinators appears to have deepened gradually across the Cretaceous period, each side shaping the other in small, incremental steps. Flowers that offered a more reliable or more accessible reward tended to attract more frequent insect visits, improving their chances of successful pollination. Insects that became more efficient at locating and exploiting these rewards, in turn, gained a more dependable food source than the older, less specialized plant groups had offered. Neither side needed to evolve with any awareness of the other for this pattern to take hold. Small advantages, repeated across countless generations on both sides, were enough to produce the increasingly close and specific partnerships that define so many flowering plants and their pollinators even now. Grasses themselves were long assumed to be a much later development. Many researchers thought they only became widespread after the dinosaurs had gone extinct. It now appears that grasses existed in at least a limited form, well before the end of the Cretaceous. Microscopic silica structures called phytoliths are produced by grasses. They have been found preserved within fossilized titanosaur dung from India. This indicates that at least some sauropods were eating grasses many millions of years before this plant family became the dominant ground cover it is today. It is a detail that continues to complicate the traditional picture of a grass-free Cretaceous landscape. Some of the largest insects ever to exist belonged to an earlier era entirely. Dragonfly relatives with wingspans far beyond anything alive today lived during the Carboniferous and Permian periods, tens of millions of years before the first dinosaurs appeared, when atmospheric oxygen levels ran much higher than they would during the age of dinosaurs itself. By the Cretaceous, insect sizes had long since settled closer to modern proportions. Beetles, cockroaches, and termites still moved through the undergrowth of every Cretaceous forest, joined now by the bees and flowering plants that would eventually come to define so much of the modern landscape. The older, non-flowering plants did not simply vanish once angiosperms arrived on the scene. Conifers, ferns, and cycads continued growing alongside flowering plants throughout the remainder of the Cretaceous, and many of these older groups remain successful today. from towering redwoods to the ferns found in almost any shaded garden. Rather than a clean replacement of one plant kingdom by another, the Cretaceous landscape gradually became a mixture of old and new. Flowering plants steadily claimed a larger share of the available ground. This was especially true in disturbed or rapidly changing environments. Their faster growth and reproduction gave them a real advantage there over their slower, more established neighbors. For much of the earlier history of paleontology, dinosaurs were generally assumed to be cold-blooded. This was largely because they were classified as reptiles. Most known reptiles at the time fit that category. That assumption has shifted a great deal since. Several lines of evidence converge here. The upright limb posture, a hallmark of dinosaur anatomy from the very start, is one of them. Another is the growing recognition that birds represent a direct continuation of the theropod lineage. Perhaps most persuasive of all is evidence drawn from bone histology. Growth rings preserved within dinosaur bones can reveal how quickly or slowly an animal grew at different points in its life. In many dinosaurs, these rings suggest a pace of growth much faster than modern reptiles achieve. Tyrannosaurus rex appears to have passed through an especially rapid growth phase during adolescence. It may have gained more than 2 kilograms of body weight per day. Growth slowed only as the animal approached adulthood. The current scientific consensus is more layered than a simple choice between cold-blooded and warm-blooded. Many researchers now believe smaller, more active theropods, closely related to birds, were likely fully warm-blooded. They would have generated their own internal heat, much as modern birds and mammals do. Some of the largest sauropods, by contrast, may have relied on a different strategy. Researchers sometimes call it gigantothermy. Sheer body size alone can help maintain a stable internal temperature this way. A larger body loses heat more slowly relative to its volume than a smaller one does. This same microscopic study of bone has occasionally revealed the biological sex of individual dinosaurs. Certain bone tissue, found in some female specimens, closely resembles medullary bone. This tissue is found today only in female birds, shortly before and during egg-laying. It serves as a temporary calcium reserve for forming eggshells. Reproduction itself varied a great deal across dinosaur groups. The evidence increasingly points away from an old assumption. Dinosaurs, it once seemed, simply laid eggs and left. Maiasaura was a duck-billed dinosaur discovered in Montana. Its name means good mother lizard. This name comes from a nesting colony the researchers found there. Nests were regularly spaced. Juvenile remains showed signs of development beyond what a newly hatched animal would display. This suggests young remained near the nest. Adults likely fed and protected them for some time after hatching. Not every dinosaur species appears to have offered this same degree of parental care. Some smaller, faster maturing species may have relied more heavily on producing large numbers of offspring, trusting that a proportion would survive on their own rather than investing heavily in any single clutch. This kind of strategy is common among many living reptiles today, and it likely worked well enough for species living in environments where predators were abundant. But food for the young was relatively easy to find without adult help. The variation across dinosaur groups, from attentive, bird-like brooding on one end to a more reptilian, high-volume strategy on the other, suggests that reproduction, much like diet and defense, was never governed by a single formula across the entire dinosaur family. A more complicated case involves the animals long known by the name Troodon. This was a small, especially well-brained theropod. Its taxonomy remains unsettled among specialists. Many fossils once attributed to this name are now reassigned or in dispute. What the fossil evidence does show clearly is a nesting pattern. Eggs sat tightly packed and upright. Comparisons with clutch structure in certain modern birds have led some researchers to propose something further. Males and females may have shared incubation duties. Oviraptorids carry their own well-known correction. The name oviraptor means egg thief. It was assigned after an early fossil was found lying atop a nest of eggs. At the time, researchers assumed the eggs belonged to a different species, one this animal had apparently been raiding. Later discoveries revealed the eggs belonged to Oviraptor itself. The animal had most likely died while brooding its own nest. Its limbs were spread protectively over the clutch, in a posture closely resembling that of many modern birds. The name was never changed. It remains attached to the fossil. A quiet record of an early, later corrected assumption. Some fossil sites preserve eggs arranged in careful, deliberate patterns. They spiral or pair in ways suggesting the adult female arranged them intentionally after laying, rather than depositing them at random. Others preserve embryos in various stages of development within the egg itself. This lets researchers study how a dinosaur skeleton formed before hatching. It also lets them estimate, through comparison with living reptiles and birds, roughly how long incubation likely lasted for a given species. One especially well-studied embryo belonged to a small oviraptorid. It was preserved curled within its shell, in a posture strikingly similar to that of a hatching bird. This suggests that at least some late-stage dinosaur embryos moved and positioned themselves before hatching. They did this much as modern chicks do. Fossilized bones sometimes show fractures that healed during an animal's lifetime rather than after death. These offer their own evidence. Dinosaurs, like most animals, sometimes suffered injury and survived it. They healed slowly over the following weeks or months. Only much later did they eventually fossilize. Some specimens even preserve signs of disease, including bone infections and what appeared to be tumors. These are conditions familiar from the study of living vertebrates. Careful comparison now makes them recognizable within animals that died tens of millions of years ago. In rare cases, fossilization has preserved far more than bone alone. A small number of specimens, generally recovered from very fine-grained sediment that buried an animal quickly, retain impressions of skin, and occasionally even traces of internal soft tissue. One especially striking example, a heavily armored nodosaur discovered in Canada, preserved not only its skin in remarkable detail, but also traces of the original pigment, letting researchers reconstruct a reddish-brown coloring across its back, likely serving as camouflage against a similarly toned Cretaceous landscape. Discoveries of this kind remain exceptionally rare, since the specific conditions needed to preserve soft tissue over such an enormous span of time rarely align, but each one offers a level of detail that bone alone could never provide. Even the size of dinosaur eggs tells its own story. Physical limits govern how oxygen and carbon dioxide pass through an eggshell. Because of these limits, Even the largest sauropods laid eggs not much larger than a football. This held true no matter how enormous the adult animal eventually became. Hatchlings across nearly every dinosaur species began life at a small fraction of their adult size. They faced a wider range of predators during their early years. This may help explain why rapid early growth proved such a consistent advantage across so many different dinosaur lineages. Judging the intelligence or inner experience of an animal extinct for tens of millions of years is a difficult task. Researchers approach it carefully. They rely on indirect evidence, such as brain cavity size and shape. They compare this against living animals, whose behavior can be studied directly. One useful measure is called the encephalization quotient. It compares actual brain size to the size expected for an animal of similar body mass. By this measure, many large plant-eating dinosaurs appear to have had comparatively small brains relative to their size. This does not necessarily mean simple or incapable behavior. Managing a very large body already demands a certain amount of neural processing on its own. Theropods generally show larger brain-to-body ratios than most herbivorous dinosaurs. Among them, the troodontids stand out. Some researchers consider their brain proportions comparable to those of certain modern flightless birds. This hints at a capacity for problem-solving or complex social behavior. It remains difficult to confirm from fossil evidence alone. Modern imaging technology has let researchers study the internal shape of dinosaur skulls in detail. This reveals which senses particular species likely relied on most. Tyrannosaurus rex shows an unusually large olfactory region. This supports the idea that smell played a major role in locating prey. It likely helped locate carcasses across long distances as well. A combination of scavenging and active hunting likely shifted with opportunity, much as it does among many living predators today. Hearing leaves its own traces. The inner ear structure of some duck-billed dinosaurs suggests sensitivity to lower frequency sound. This connects naturally to one of the more distinctive features of this group. Parasaurolophus carried a long, curved, tube-like crest extending back from its skull. This crest was hollow. It looped internally in a way that resembles the tubing of a brass musical instrument. Reconstructions built from this internal structure generally produce a low, resonant sound. This suggests that at least some duck-billed dinosaurs used vocal cords to communicate across distance. They may have identified individuals within a herd this way. They may have signaled alarm too. Trackway evidence supports the idea that herding was common among plant-eating dinosaurs. Some sites contain dozens of parallel sauropod footprints moving in the same direction. This suggests coordinated group movement. At one especially well-studied site in Texas, smaller footprints cluster toward the center of the group's path. Larger footprints line the outer edges. Some researchers interpret this as a protective arrangement, shielding younger or smaller individuals. Bone beds reinforce this picture. Some sites contain the remains of dozens or hundreds of Centrosaurus individuals. This suggests substantial herds. Some of these may represent entire groups lost together during a single event, such as a flash flood while crossing a swollen river. Group living was not limited to the largest, most familiar herding dinosaurs. One especially striking fossil, recovered from China, preserves a group of 34 young Psittacosaurus individuals all roughly the same age, found together in a single mass. Researchers interpret this as evidence that at least some early ceratopsians formed close social groups even at a young age, well before reaching adult size, whether under the watch of a parent or simply through the safety that comes from staying close to siblings and peers. It suggests that social behavior among plant-eating dinosaurs may have begun earlier in an individual's life than the herding evidence for fully grown adults alone would suggest. Evidence for cooperative hunting among predatory theropods remains much less certain than the evidence for plant-eater herding. Multiple individuals found together at a single site could reflect genuine cooperative behavior. They could also reflect several animals independently drawn to the same carcass. Popular depictions often show large predators hunting in tightly coordinated packs. The fossil record supports this specific claim only weakly. Researchers remain divided on how much organized cooperation, if any, actually occurred. A separate line of evidence involves tooth marks found on the bones of some theropods. These match the spacing of teeth from the same or a closely related species. This has led some researchers to suggest occasional feeding on members of one's own species. This could reflect active conflict or opportunistic scavenging of an already dead individual. This behavior is documented among a range of living predators as well. Hearing and vocal communication likely extended well beyond the resonant calls of crested hadrosaurs. The inner ear structures of various theropods suggest a hearing range broadly comparable to that of modern birds. An enlarged trachea shows up in some specimens too. This hints that low-frequency calls, similar to those produced by large modern birds such as cassowaries, may have been more widespread across the dinosaur family. The fossil evidence for any single species cannot fully confirm this on its own. Some dinosaur populations lived at genuine climatic extremes. During parts of the Cretaceous, southeastern Australia sat much further south than it does today. It lay within or near the polar circle. This meant extended winter darkness for weeks or months at a time. Fossils from this region include the small dinosaur Lialinsaura. Its eye sockets are unusually large relative to skull size. This was likely an adaptation for low-light conditions. Most researchers lean toward the view that these polar dinosaurs remained active through the winter. Migration away or dormancy seems less likely. The question is not fully settled. Migration more broadly remains an area of active but incomplete research. Isotope analysis examines chemical signatures in teeth and bone. These signatures vary somewhat by region. In some cases, this has suggested that certain large Cretaceous herbivores moved across a meaningful range of distance during their lives. Researchers remain cautious about how confidently this evidence should be read. A number of other factors can influence isotope patterns. Vision has left its own trace in the fossil record. A ring of small bones, called the sclerotic ring, sits within the eye socket of many dinosaur skulls. Its size and shape can offer clues about whether an animal was more active during the day or during low light. This comes from comparisons with the same structure in living reptiles and birds. Several small theropods, based on this evidence, appear to have been active during dusk, dawn, or even parts of the night. This ability would have suited a predator hunting in dense undergrowth. It would also help one avoid the attention of larger, daytime rivals. Color vision, inferred largely through comparison with living birds and reptiles, may have extended into ranges beyond typical mammalian perception. This includes some sensitivity to ultraviolet light. It would help explain why so many feathered dinosaurs appear to have developed patterned, colorful markings, clearly meant to be seen by others of their kind. The picture that emerges across this chapter is one of considerable sensory variety, matched carefully to each animal's particular way of life. A scavenging tyrannosaur relied heavily on smell, sweeping across long distances in search of a carcass. A herding hadrosaur relied on sound, calling out through a resonant crest to keep track of its group across an open floodplain. A small nocturnal theropod relied on sharp night vision, moving quietly through undergrowth that would have hidden it from larger daytime predators. No single sense dominated across the dinosaur family as a whole. Each lineage, shaped by its own particular pressures, developed the particular combination of senses best suited to keeping it alive. By the late Cretaceous, roughly 100 to 66 million years ago, the dinosaur world had reached its final and most diverse form. Among its predators, none is more familiar than Tyrannosaurus rex, though this animal actually appears surprisingly late in the story. Tyrannosaurus lived only during the final 2 or 3 million years before the extinction event that closed the era. A wider stretch of time separates Tyrannosaurus from Stegosaurus, a dinosaur it is often pictured alongside, than separates Tyrannosaurus from the present day. Research into Tyrannosaurus biology has revealed an animal far more capable than its size alone would suggest. Its bite force ranks among the strongest recorded for any land animal. It was strong enough to crush bone rather than simply cut through soft tissue. This let it consume parts of a carcass most other predators would leave behind. Fossilized droppings attributed to the species contain crushed bone fragments. These support this conclusion directly. Its unusually developed sense of smell likely let it combine active hunting with long-distance scavenging as circumstances allowed. Some specimens show healed bite wounds matching the size of other Tyrannosaurus teeth. This hints at conflict, quite possibly with rivals of the same species. One detail of Tyrannosaurus anatomy has puzzled researchers for decades: its unusually short arms, tiny relative to its enormous head and powerful legs. Several explanations have been proposed. The arms may have helped an animal push itself upright after lying down, a task made difficult by such a heavy head and body. They may have assisted in gripping struggling prey at close range, even if they played little part in actually killing it. Whatever their exact function, the arms were far from useless. Each retained 2 clawed fingers, and the bones show attachment points for real muscle, suggesting they still did some work, even if that work remains harder to pin down than the more obvious power of the jaws. Tyrannosaurus was the last and largest member of a family that had been diversifying for tens of millions of years before its appearance. Earlier and generally smaller tyrannosaurs hunted across river deltas and coastal plains. During the millions of years leading up to Tyrannosaurus itself, Albertosaurus and Gorgosaurus, both from North America, are 2 examples. Trackway and bone bed evidence associated with some of these earlier relatives has been interpreted by certain researchers as possible support for some degree of group behavior among tyrannosaurs more broadly, though this remains an area of active debate rather than settled consensus. The same caution warranted for similar claims about other theropod groups. Some researchers propose that Tyrannosaurus itself descended from smaller tyrannosaur relatives known from Asia, which may have crossed into North America at some point during the late Cretaceous, though the exact details of this ancestry remain an open question rather than an established fact. If accurate, it would be one more sign of how continental connections, however temporary, continued to shape dinosaur evolution, even this late in the Mesozoic era. Titanosaurs were the last major branch of the sauropod lineage. They reached the greatest sizes of any land animal known from the fossil record. Argentinosaurus, from what is now Argentina, may have exceeded 30 meters in length. The incomplete nature of its remains leaves considerable uncertainty around exact figures. These animals persisted across much of the late Cretaceous world. They were a final expression of the sauropod body plan, first emerging over 100 million years earlier. Unlike many of their Jurassic ancestors, Titanosaurs appear to have carried armor of their own, a feature largely absent from earlier sauropod groups. Small bony plates, called osteoderms, have been found associated with several titanosaur species, embedded in the skin along the back in a manner recalling, on a much smaller scale, the armor carried by ankylosaurs. Whether this armor offered meaningful protection against the large predators of the late Cretaceous remains uncertain. It may instead have served some other purpose, such as calcium storage. Even so, its appearance specifically within this later branch of sauropods suggests it developed in response to threats that earlier Jurassic sauropods simply had not faced in the same way. Far to the east, in what is now Mongolia, a very different landscape supported its own distinctive late Cretaceous fauna. The Gobi Desert region preserves an environment of shifting sand dunes and sudden, violent sandstorms. These conditions occasionally buried animals rapidly enough to preserve exceptional detail. One especially well-known fossil captures a moment of direct conflict. A velociraptor and a plant-eating Protoceratops were found locked together. They had apparently been buried mid-struggle by a collapsing dune. The raptor's sickle claw sits positioned against its opponent's throat. Velociraptor itself was much smaller than popular depictions often suggest. It was closer in size to a large turkey than to the pack-hunting predators of film. Evidence for organized group hunting in this species remains as debated as it does for its North American relative, Deinonychus. The late Cretaceous also saw ceratopsians, the horned dinosaurs, reach their greatest diversity. Triceratops is the most familiar member of this group. It carried 3 prominent horns and a wide bony frill extending back over the neck and shoulders. The frill's purpose remains debated. It may have offered some protection during confrontations. It likely played a role in visual display too, since frill shape and ornamentation varied noticeably between related species. Fossil skulls sometimes bear healed puncture wounds, matching the spacing of Triceratops' horns. This suggests these animals sometimes used their horns against each other. Contests over territory or over mates seem the likely cause. A close relative, Torosaurus, carried an even longer, more elaborately fenestrated frill. Its relationship to Triceratops remains an open question that has not been settled. Some researchers propose that Torosaurus is not a separate species at all, but instead represents the fully mature adult growth stage of Triceratops itself, with the distinctive frill openings developing only late in life. This hypothesis remains debated rather than settled fact, and it shows how markedly a single species can look different at different points in its life, especially around display structures such as horns, frills, and crests. Triceratops and Torosaurus were far from the only ceratopsians roaming the late Cretaceous landscape. Styracosaurus carried a ring of long, spike-like horns radiating outward from its frill, along with a single prominent horn on its nose, an arrangement clearly built as much for display as for defense. Pachyrhinosaurus took a different approach entirely, replacing a pointed nose horn with a thick, rough, bony boss, a shape unlike almost any other ceratopsian known. Bone beds containing large numbers of Pachyrhinosaurus individuals, some interpreted as entire herds caught together in a single catastrophic event, suggest this animal shared the same tendency toward group living seen in Centrosaurus and its relatives. Across all of these species, the underlying skull and frill remained broadly similar in basic structure. What varied was the specific arrangement of horns, spikes, and bosses from one species to the next. This fits naturally with an idea researchers hold about these features. They may have served largely as a means of visual identification. Individuals could recognize their own species this way, and quite possibly their own particular herd, at a glance. Duck-billed dinosaurs, or hadrosaurs, reached similar diversity during this period. They are distinguished largely by the shape of their skull crests. Some, like Parasaurolophus, carried a long, resonant, tube-shaped crest. Others carried simpler, solid crests instead. Their dental batteries made them some of the most efficient plant processors of the entire Mesozoic era. Edmontosaurus was a crestless hadrosaur from the very end of the Cretaceous. It is known from several so-called mummified specimens. These are skeletons preserved alongside impressions of the surrounding skin. This reveals a covering of small, pebbly scales across most of the body. A possible remnant of a soft, fleshy coxcomb sits on the head. This detail is impossible to determine from bone alone. Hadrosaurs appear to have lived in some of the largest herds of any late Cretaceous dinosaur. Extensive trackway and bone bed evidence supports this. Certain sites in North America preserve the remains of many thousands of individuals within a single bone bed. This likely represents a herd overtaken by a sudden flood or a similar catastrophic event while migrating or gathering along a river system. Ankylosaurs first appeared in the Jurassic. They reached their fullest expression in the late Cretaceous. Some members of this group, the Ankylosaurids, carried a heavy, rounded club of fused bone at the end of a stiffened tail. Bone structure analysis suggests this club could deliver blows strong enough to fracture the leg bones of an attacking predator. Their low, wide, heavily plated bodies left few unprotected areas for a predator to target. Not every ankylosaur carried a tail club. A related family, the Nodosaurids, relied instead on heavier body armor, and in some species, long shoulder spikes, without ever developing the swinging tail weapon seen in their ankylosaurid cousins. This split within the broader ankylosaur family suggests two somewhat different defensive philosophies developed side by side, one built around active, offensive use of the tail, and the other built around passive endurance, simply presenting a predator with as little vulnerable surface as possible and waiting for the threat to lose interest. A separate and stranger defensive strategy appeared among the pachycephalosaurs. These were small herbivores or possibly omnivores. They are known for the thick, domed bone forming the top of the skull. In some species, this exceeded 20 centimeters in solid thickness. Early researchers generally assumed this dome existed for direct, head-on combat between rivals. More recent analysis has introduced doubt. The internal bone structure may not have withstood repeated high-force impact without risking injury. Some researchers now propose less forceful flank-shoving contests instead. Others propose a primarily visual display function. A related debate concerns Dracorex, a flat-skulled pachycephalosaur relative covered in bony knobs and spikes. Some researchers argue this represents not a distinct species, but a juvenile growth stage of a different, already known pachycephalosaur. Its domed skull, under this idea, simply had not yet developed. As with the Triceratops and Torosaurus question, this remains an open hypothesis rather than settled fact. The late Cretaceous world, as a whole, supported a greater density and diversity of large plant-eating dinosaurs than any earlier period of the Mesozoic. Ceratopsians, hadrosaurs, ankylosaurs, and titanosaurs often shared overlapping ranges within a single ecosystem, each specialized enough in its feeding strategy, height, or preferred vegetation to avoid direct competition with its neighbors. This layered, tightly packed community of herbivores, in turn, supported an equally layered predator community, running from apex hunters like Tyrannosaurus down through a range of smaller theropods filling every remaining niche the ecosystem allowed. The sheer variety of hadrosaur crest shapes deserves a closer look on its own, since it illustrates how much diversity a single basic body plan could produce once display, rather than defense or feeding, became the main pressure shaping a particular feature. Lambosaurus carried a hatchet-shaped crest, quite different in outline from the long curved tube of Parasaurolophus. Corythosaurus carried a tall, rounded crest resembling a dinner plate set on edge. Each shape would have produced a slightly different resonant sound when air passed through it, and each would have looked distinct from a distance, letting individuals of different species or different sexes within the same species recognize one another at a glance across an open floodplain. In the final few million years before the Cretaceous period ended, a broad floodplain environment covered much of what is now western North America. Slow-moving rivers threaded through it, along with conifer stands and stretches of flowering vegetation. This world would have been unrecognizable to any dinosaur living even 20 million years earlier. Tyrannosaurus rex hunted here. Triceratops and its relatives lived alongside it. Duck-billed dinosaurs moved in herds along the river margins. Ankylosaurs grazed low, dense vegetation near the water's edge. This ecosystem is preserved today largely through a rock formation called Hell Creek. It offers one of the most complete windows available into any single moment of the dinosaur age. Layer upon layer of bone, plant matter, and trackway evidence built up across the final stretch of the Mesozoic era. Seasonal rains would have swelled the rivers. They carried sediment across the floodplain. This buried the remains of animals that died near the water. However unintentional, this process preserved an unusually detailed record. It shows exactly what this world looked like in its last few 100,000 years. Small mammals moved through the undergrowth of this world as well. Most were nocturnal. Most were no larger than a modern rat. They shared the forest floor with early relatives of salamanders, turtles, and crocodilians. Unlike so many of their dinosaur neighbors, these animals would go on to survive what was coming. Flowering plants, by this point, had come to dominate much of the ground cover and understory. Surviving stands of conifer and fern remained too. together, this formed a landscape significantly closer in general appearance to a modern subtropical forest than to the fern-dominated world of the early Mesozoic. The rivers and wetlands of this landscape supported a surprising range of turtle and crocodilian species, some of them barely changed from their modern descendants. Champsosaurus, a long-snouted, crocodile-like reptile that was not actually a true crocodilian at all, hunted fish in these same waterways, part of a broader reptile community that extended well beyond the dinosaurs themselves. Several turtle species, some reaching a considerable size, shared these rivers as well, their shells occasionally preserved in remarkable detail alongside the bones of the dinosaurs that once waded past them. This wider community of smaller, less famous animals rarely receives the same attention as Tyrannosaurus or Triceratops, but it filled out an ecosystem that was, in its full complexity, significantly richer than any single headline species could suggest on its own. This North American floodplain was far from the only ecosystem operating on the eve of the extinction. In Mongolia, the Nemeg Formation preserved its own final community of tyrannosaurs, titanosaurs, and ornithomimosaurs. They moved through a landscape of braided river channels, quite different in detail from the Hell Creek floodplain. Even so, its underlying structure was broadly similar. This was a settled, diverse dinosaur fauna showing no obvious sign of decline. Similar snapshots exist from South America, India, and parts of Europe. These scattered final ecosystems, taken together, paint a consistent picture. Wherever paleontologists have found rock layers from the last few 100,000 years of the Cretaceous, dinosaur communities appear to have remained rich, varied, and stable, right up until the moment the fossil record abruptly stops. Nothing in the fossil record suggests this world was in any particular decline. Dinosaur diversity in these final ecosystems appears to have remained broadly stable. Predators, herbivores, and smaller animals continued much as they had for millions of years before. Whatever difficulties lay ahead, they did not arrive gradually. Nothing in the geology of this period gave any advance warning of what was coming. Researchers have spent considerable effort testing this exact question, since it carries real weight for understanding what actually happened at the extinction itself. If dinosaur diversity had already been quietly declining before the impact, for reasons unrelated to the asteroid, that would suggest a rather different story from a healthy, stable world struck down suddenly and without warning. The most detailed studies of the Hell Creek Formation and similar sites, examining the full range of species present across the final several 100,000 years before the boundary, have generally found no clear signal of decline. Some individual groups may have fluctuated in relative abundance, as any ecosystem naturally does from one period to the next, but the overall picture remains one of a rich, functioning dinosaur world, still very much intact, right up until the very end. 66 million years ago, at the boundary between the Cretaceous and the following Paleogene period, an object struck the Earth. It measured roughly 10 to 12 kilometers across. It hit what is now the Yucatan Peninsula in modern-day Mexico. The impact left behind a crater now buried beneath later layers of sediment. Researchers estimate it at somewhere between 150 and 200 kilometers across. Detailed geological surveys confirmed it during the latter part of the 20th century. Near the impact site, the immediate effects would have included intense heat. fires will have spread across a wide surrounding region. A large displacement wave moved outward from the point of impact, since the strike occurred in a shallow coastal sea. Geological deposits along the Gulf Coast of what is now the United States preserve evidence consistent with this wave. Layers of jumbled sediment and displaced marine debris were laid down within hours of the impact. This offers a rare, direct physical record of the event's earliest and most immediate consequences. The more significant global effects came from something else entirely. An enormous volume of pulverized rock and sulfur-rich material was thrown high into the atmosphere. Much of it appears to have spread around the planet within weeks or months. This blocked a meaningful portion of incoming sunlight for an extended period. The reduction in sunlight suppressed plant growth and photosynthesis on a global scale. It collapsed the base of the food chain. Disruption rippled outward through nearly every ecosystem on Earth. Researchers studying sediment layers from this period have made estimates about how long this lasted. The most severe disruption to sunlight and plant growth may have lasted somewhere between several months and a small number of years. This is a relatively brief window in geological terms. It was still long enough to unravel food chains. Those chains had depended on a steady, uninterrupted supply of plant growth to support the animals further up the chain. The impact did not act entirely alone. During roughly the same broad stretch of geological time, a massive series of volcanic eruptions was underway in what is now India. These produced a layered volcanic rock formation known as the Deccan Traps. The eruptions released substantial quantities of gas into the atmosphere over an extended period. Some researchers propose that this ongoing volcanism may already have been placing stress on global ecosystems before the impact occurred. The precise balance of responsibility between the asteroid and the Deccan Traps remains an active area of research. Even so, the impact is generally regarded as the primary and most immediate trigger for the extinction that followed. The evidence tying this extinction directly to the asteroid impact rests on more than the Chicxulub crater alone. A thin layer of sediment found at the same geological boundary in rock formations around the world contains an unusually high concentration of iridium, an element rare on the Earth's surface but common in many asteroids and comets. This layer was first identified and connected to the extinction in the late 1970s. It provided some of the earliest strong evidence that something had struck the planet. At precisely this moment in time, its presence on multiple continents matters a great deal. It sits within rock laid down at the same narrow point in geological history. This remains one of the clearest single pieces of evidence supporting the impact hypothesis. The consequences for non-avian dinosaurs were close to total. Every known species vanishes from the fossil record, at or very near this boundary layer. This happened within an extremely narrow window of geological time. Pterosaurs disappeared entirely. So did the last of the plesiosaurs. A substantial share of marine life more broadly disappeared too, including the ammonites, a group of coiled, shelled sea creatures that had thrived across the oceans for hundreds of millions of years. Not every group suffered equally, and understanding why helps clarify what actually happened. Smaller animals generally fared better than larger ones, likely because smaller bodies require less food, an advantage in a world where plant growth had been sharply disrupted. Animals capable of surviving on a flexible diet also appear to have had better odds, including those that could rely on seeds or scavenged material rather than a single, narrow food source. Freshwater environments seem to have offered better odds of survival too, buffered somewhat from the most severe effects of sunlight loss by the organic matter already present in rivers and lake beds compared to either the open ocean or the exposed land surface. This may help explain why crocodilians, turtles, and various freshwater fish came through this period in comparatively good standing. This is where the surviving branch of the dinosaur family becomes significant. Birds are, in the most direct biological sense, small feathered theropod dinosaurs. It was specifically this small-bodied flexible branch that survived the extinction. Every non-avian dinosaur lineage did not, regardless of size or specialization. The age of the dinosaurs did not end quite as completely as it is sometimes described. It ended for every large, ground-dwelling lineage covered so far, while one small, quiet corner of that same family tree slipped through, carrying the story forward. The scale of what was lost at this single boundary is worth sitting with for a moment. Every dinosaur lineage covered so far in this history, the towering sauropods, the armored stegosaurs and ankylosaurs, the horned ceratopsians, the crested hadrosaurs, and the great predatory theropods including Tyrannosaurus itself, came to an end within the same narrow window of geological time. Groups that had taken well over 100 million years to diversify into such an enormous range of forms disappeared within what geologists measure as an instant. A stark illustration of how quickly even the most successful and deeply established forms of life can be undone. When the disruption is severe enough and arrives with no opportunity for gradual adaptation. The years immediately following the extinction would have been difficult to witness, had anyone been present to witness them. So many large plant-eating and predatory species were suddenly gone. Ecosystems across the planet entered a long period of imbalance. Surviving species gradually adapted to fill the ecological gaps left behind. Mammals had existed alongside dinosaurs for the entire Mesozoic era without growing especially large, generally remaining small and modest in size throughout. Once so many of their larger Mesozoic competitors had disappeared, mammals began a period of comparatively rapid diversification. Within a small number of millions of years, mammal lineages grew larger and diversified into many of the broad groups still recognizable today, including the early ancestors of horses, whales, and primates. Some of the earliest large mammals to appear in the aftermath belonged to a group called pantodonts, which reached the size of a small hippopotamus within just a few million years of the extinction. A striking pace of change given how consistently small mammals had remained throughout the entire preceding age of dinosaurs. The framing here deserves some care. Mammals were not simply held back by dinosaurs waiting for their chance. The ecological space of the Mesozoic world had already been thoroughly divided among an enormous range of established dinosaur species, leaving comparatively little room for larger-bodied mammals. Once that structure was suddenly disrupted, the space truly opened, and mammals, already present and reasonably diverse in their own smaller way, were positioned to expand into it. Birds followed a distinctly different path through this same transition. They had already been a recognizable part of Mesozoic ecosystems for tens of millions of years before the extinction occurred. A small number of bird lineages survived. These survivors experienced their own considerable diversification, during the early part of the following geological era. Eventually, they produced the broad range of modern bird groups recognizable today. This ranges from tiny hummingbirds to large flightless birds, such as ostriches and emus. Among the earliest post-extinction birds were large, flightless, predatory forms. These briefly filled some of the ecological space left vacant by the disappearance of small and mid-sized theropod dinosaurs. They hunted on foot across the open landscapes of the early Paleogene, before mammals grew large and diverse enough to take over that particular role. Plant life, too, took time to recover its earlier balance. In the immediate aftermath of the extinction, fern spores dominate the pollen record found in rock layers from this period, a pattern also seen after more recent volcanic disasters, where ferns are often among the first plants to recolonize a damaged landscape. This so-called fern spike gradually gave way, over the following tens of thousands of years, to a slower return of more diverse forests, as flowering plants and conifers re-established themselves across the recovering landscape. The pace of this recovery varied significantly from region to region, and in some areas, forest diversity does not appear to have fully rebounded to its pre-extinction level for several 100,000 years. The climate of this period is generally called the early Paleogene. It differed from what had come before. Global temperatures during parts of this era reached levels warmer even than the already warm Cretaceous. This included a pronounced warming episode known as the Paleocene, Eocene, thermal maximum, around 56 million years ago. Researchers still study this event for insight into the causes and effects of rapid climate change more broadly. Across the many millions of years that followed, continents continued drifting toward their current positions. Mountain ranges continued rising, including the Himalayas, formed by India's eventual collision with Asia. The global climate gradually shifted toward the cooler, more strongly seasonal pattern. This pattern would eventually give rise to the ice ages of the more recent geological past. The oceans, too, needed time to recover their earlier balance. The ammonites and many other marine groups had vanished at the boundary, alongside the last of the great marine reptiles. In their absence, new groups of fish and early marine mammals gradually expanded to fill the resulting gaps. Though this process unfolded across millions of years rather than happening all at once. Coral reefs, badly disrupted by the ocean chemistry changes that followed the impact, took an especially long time to fully recover, with some estimates suggesting reef ecosystems did not return to anything resembling their former diversity for several million years after the extinction itself. None of the detail explored across this documentary would exist without a slow, often accidental process. Dinosaur fossils have been discovered and studied over the past 2 centuries. Long before the word dinosaur existed, large fossilized bones occasionally surfaced. Farmers, quarry workers, and other people going about ordinary life found them. These finds were interpreted at times through local folklore. Occasionally, people attributed them to giants or to dragons. The concept of an ancient, unrecorded extinct animal had not yet taken hold as an accepted scientific idea. This began to change in the early 19th century, largely through the work of a small number of dedicated collectors in England. Mary Anning worked as a fossil collector along the coastal cliffs near Lyme Regis. She made a series of important discoveries, despite working largely outside the formal scientific institutions of her time. These included detailed ichthyosaur and plesiosaur skeletons, providing crucial early evidence for extinct marine reptiles. Anning's contributions were, for much of her lifetime, under-recognized by the male-dominated scientific establishment. Even so, her work is now widely regarded as foundational to the early development of paleontology. Around the same period, a physician named Gideon Mantell began collecting large fossilized teeth. He worked with his wife, Mary Ann Mantell. The teeth came from a quarry in southern England. Mantell eventually concluded they belonged to an enormous, previously unknown plant-eating reptile. He named it Iguanodon, drawing a comparison between these fossil teeth and the smaller teeth of a modern iguana. Mantell's interpretation faced considerable resistance from established figures in the scientific community. This pattern was common throughout the early history of the field. Entirely new categories of animal had to be argued for, against the weight of existing assumptions. It was the English anatomist Richard Owen who formally coined the term Dinosauria in 1842. The name means terrible lizard. He drew Iguanodon together with other similarly enormous fossil reptiles, identified around the same period, into a single, newly recognized group. He correctly identified shared skeletal features, setting these animals apart from all other known reptiles. Fossil discovery accelerated through the latter half of the 19th century, especially in North America. A bitter rivalry emerged there between paleontologists Othniel Charles Marsh and Edward Drinker Cope. People sometimes call it the Bone Wars. It drove both men to fund extensive fossil hunting expeditions across the American West. This resulted in the description of many now familiar species, including Stegosaurus, Triceratops, and Allosaurus. The intensity of their competition also led to some rushed work, which later researchers had to carefully untangle. Fossil hunting has continued expanding ever since. It now extends across nearly every continent, including significant and ongoing work in China, Mongolia, and Argentina. These regions received comparatively little attention from the largely European and North American paleontological community of earlier generations. One especially notable early expansion came during the 1920s. A series of expeditions led by the American explorer Roy Chapman Andrews traveled into the Gobi Desert of Mongolia. They had initially set out searching for evidence of early human origins. Instead, they uncovered some of the richest dinosaur fossil beds ever found. These included the first confirmed dinosaur nests and eggs belonging to Protoceratops. They also included the original Velociraptor specimens. These expeditions were often mounted with camel caravans and early motor vehicles across difficult, remote terrain. They opened an entirely new region of the world to systematic paleontological study. That region continues to yield significant discoveries today. Many of the most detailed recent discoveries have come from precisely these more recently explored regions, including the feathered dinosaur specimens covered in an earlier chapter of this history, meaningfully revising the picture first established by earlier researchers. Modern paleontology has been transformed by technology unimaginable to 19th century researchers. Computed tomography scanning allows examination of fossil interiors without any physical cutting. Chemical analysis has, in a handful of exceptional cases, detected traces of original proteins or pigment, bearing structures. This is within fossils tens of millions of years old. Digital modeling now lets researchers test hypotheses about movement, bite force, and sound production. Earlier generations, working only with physical specimens and careful comparison, simply could not do this. Amber, the fossilized resin of ancient trees, has provided its own distinctive window into this world, preserving small organisms with a level of three-dimensional detail rarely matched by any other kind of fossil. Insects trapped in Cretaceous amber sometimes retain fine details down to the individual hair on a leg. In a small number of remarkable cases, amber has even preserved fragments of dinosaur material directly. One example is a feathered dinosaur tail found encased in amber from Myanmar, complete with individual barbs and barbules still visible under magnification. Discoveries of this kind offer a level of preservation that ordinary rock-hosted fossils, however well preserved, simply cannot match, since amber can capture the finest structural detail of an object almost at the moment it became trapped. New species continue to be described at a steady pace even now. Often they come from regions only recently opened to sustained paleontological survey. Museum collections gathered decades ago sometimes yield fresh discoveries as well. A specimen collected for one purpose is occasionally re-examined with modern tools. Sometimes it turns out to belong to a species no one had previously recognized. Some individual fossil discoveries have taken on a significance beyond their scientific value alone. In 1990, a fossil hunter named Sue Hendrickson discovered one of the most complete Tyrannosaurus rex skeletons ever found in South Dakota, a specimen that came to be known informally by her own first name. Its recovery led to a lengthy legal dispute over ownership, eventually resolved through a public auction, where the skeleton sold for a sum well beyond what most dinosaur fossils had ever commanded before. The case drew wide public attention to questions that had, until then, remained largely internal to the paleontological community. These included who has the right to excavate and sell fossils found on private or tribal land. They also included how museums can realistically compete for specimens of such significance against private collectors and institutions with far greater financial resources. Despite this progress, the fossil record remains incomplete by its very nature. Fossilization requires a fairly specific set of conditions. Generally, this means rapid burial shortly after death. The overwhelming majority of dinosaurs that ever lived left no trace at all. Everything currently understood about dinosaurs represents a partial, carefully reconstructed glimpse into a far larger history. It is one still being filled in, one fossil discovery at a time. Not every significant find has come from a trained paleontologist working a planned excavation. Ordinary walkers, ranchers, and amateur collectors have stumbled across important specimens simply by noticing an unusual shape weathering out of a hillside or a riverbank in various parts of the world over the past 2 centuries. Many countries now have clear guidelines for what to do in such a case, generally encouraging the finder to leave the specimen undisturbed and contact a local museum or university, since careless removal can destroy information that a trained excavation would otherwise preserve. This ongoing collaboration between professional researchers and the wider public continues to add new pieces to a puzzle that, after 2 centuries of careful work, remains far from complete. Step outside and look at an ordinary bird resting on a fence post. You are looking at a living dinosaur. It is not a distant relative, and it did not descend from dinosaurs in some loose, indirect sense. It is a direct continuation of the theropod lineage, carrying forward, in modified form, many of the same basic features first developed by its Mesozoic ancestors. The hollow, air-filled bones carried by sauropods and other large dinosaurs remain present in modern birds, reducing body weight while maintaining structural strength, especially useful for an animal that needs to become light enough for sustained flight. The internal air sac system, present in dinosaurs as far back as the Triassic, remains a defining feature of the modern bird respiratory system, allowing an unusually efficient, one-directional airflow through the lungs, more effective at extracting oxygen than the simpler, back-and-forth breathing used by mammals. This same efficient breathing system is thought to help birds survive at high altitudes where oxygen is scarce, and to sustain the enormous energy demands of long migratory flights, capacities tracing back to a respiratory adaptation that first appeared over 200 million years earlier for entirely different reasons. The scaled skin found on the legs and feet of modern birds is a direct holdover from their reptilian ancestry, a small trace of the deeper connection between birds and the wider reptile family tree, of which dinosaurs were simply one especially successful branch. Even the furcula, the fused wishbone found in the chest of most modern birds, has a direct fossil history, appearing first among certain theropod dinosaurs long before flight existed, likely serving originally as an anchor point for arm and shoulder muscles used in grasping prey, and only later taking on its familiar role in supporting the mechanics of flapping flight. The attentive nesting and brooding behavior seen in many bird species closely mirrors the behavior of Maiasaura, Troodon, and the oviraptorids, a pattern that stretches back well over 100 million years and continues largely unbroken into the present. Even the way a chick pecks its way out of an egg using a small temporary bump called an egg tooth appears to reflect a shared solution to hatching, one likely present in dinosaur eggs long before birds themselves existed in anything like their modern form. None of this connection is metaphorical, and it is not simply a poetic way of describing a shared ancestry. Birds are dinosaurs in the same direct technical sense that a human being is a mammal, or that a trout is a fish. The classification reflects an unbroken line of descent, traceable through an increasingly detailed fossil record, stretching back across the entire span of time covered in this history. Roughly 11,000 species of birds share the planet today, occupying nearly every environment available to them, from dense rainforest canopies to the open ocean, from high mountain slopes to city rooftops. A diversity that quietly exceeds the total number of dinosaur species known from the entire fossil record combined. An ordinary sparrow or pigeon, moving through a park with no particular fanfare, carries the same deep history as any of the family's more famous names. The same hollow bones, the same efficient lungs, the same basic body plan, first tested by small theropods long before anyone could have guessed where it was headed. The age of dinosaurs was never one story. It was many stories, unfolding together across more than 160 million years. This all happened on a planet that continually reshaped itself beneath them. Some dinosaurs lived their entire lives within sight of the equator. Others endured months of near-total winter darkness near the ancient polar circle. Some dinosaurs were the size of a small dog. Others were so large that a single footprint could have held an adult person standing comfortably inside it. Some animals were covered in scales. others were covered in feathers, patterned with colors. Researchers can now reconstruct with real confidence, drawn from structures preserved within the fossil record itself. Some animals lived and died largely alone. Others moved together in herds, numbering into the hundreds, watching over their young across long seasonal journeys. There were careful parents, brooding over their nests in postures that would not look out of place among birds today. There were animals built almost entirely around speed, size, or armor, the simple advantage of outlasting whatever difficulty the ancient world placed in front of them. There were minds capable, in at least some cases, of a kind of problem-solving and social awareness we are only beginning to understand. There were senses tuned with real precision to smell, sound, and sight, each suited to an animal's particular place in its world. Then, in a single sudden moment, so much of that long story came to an end. It did not happen through gradual decline. A catastrophic event arrived instead, without warning, from beyond the planet itself. Yet even here, the story does not fully end. A single branch continued. It carried forward the same essential blueprint developed over 100 million years earlier. Slowly, it filled the world with an entirely new range of forms. These are the birds that now move through forests, cities, coastlines, and open skies across almost every corner of the modern world. So much of what feels permanent in the natural world was, at some earlier point, built across an almost unimaginable span of time. Countless small adjustments made this possible, each one barely registering on its own, adding up across many millions of years into this long, layered history. The world continues to change, just as it always has. It changed from the dry interior deserts of Pangaea to the shallow, warming seas of the late Cretaceous. It is changing still. And somewhere, resting on a branch outside a window, a small feathered descendant of that same story carries on. It is a living, breathing continuation of the age of dinosaurs, present in this ordinary moment, and very likely in the next.